In this video, we'll solve a differential equation. It'll turn out to be first order with homogeneous coefficients, and we'll apply a substitution method in order to turn it into a separable differential equation. As it stands right now, I see dy dx. That's the highest derivative, so it's first order. And then on the right hand side is some rational expression, and I've said that x is not equal to 0, presumably because of this x in the denominator here. Now, I'm just going to naively try to separate the variables first to see if it's separable. So I'm going to separate the dy and the dx as we would usually do and write it in differential form. So I have x times dy, I'll bring the x over, is equal to x minus y times dx. And you can see the problem is that I have a difference here. I don't have a product of things that I can factor into x's and y's. I can't separate the x and y here. They're in two different terms, and so you're never going to be able to separate the variables. Let's bring everything to one side. So I'm going to bring that first term over to the other side and subtract the other one over. So I'll have a dx term and a dy term. And the key here is to recognize that this coefficient of dx is homogeneous of degree 1. I'm seeing degree 1 here, degree 1 in y, and I'm seeing degree 1 in x here. I'm not squaring something and not squaring the other thing. Everything is linear in x's and y's. So these coefficients are homogeneous of degree 1. I'm just focusing on the x minus y. That's degree 1, degree 1. I look at the other coefficient, the minus x, that's degree 1. So that suggests that I should try a substitution. What we'll do is we'll let y equal to u times x, where u is some new variable. And if I'm going to do that, I need to substitute out the dy as well here. So I'll calculate dy. That requires using a product rule, and in differential form, that will look like u times dx plus x times du. So I essentially leave one alone, and I take the differential of the other one. And then I, in the second term, switch it around. That's just the product rule in differential form. So now we carry out this substitution. I've got x minus y, which becomes u times x instead. I'll have dx, and then minus x. And then for dy, I have to put this complicated product rule expression. And on the right-hand side, I still have equal to 0 here, so equal to 0 there. Now, what is always going to happen in this situation is you'll be able to do some factoring. You'll be able to factor out a common power, in this case a power of x. So I'm going to factor out the x that appears over here. I'll have x and there'll be 1 minus u, and everything else will stay the same. And because of the fact that I had an x in my substitution, I was able to factor out that x here and match it with the x here. I'll be able to cancel out that common factor. And when I do that, I'll have 1 minus u here, and then on the second term, everything that was in the brackets already, I've canceled out that power of x that appears. Notice that's okay to do. I divided by x, and x is not 0. We've stipulated that ahead of time. So I'm not dividing by 0 by doing that. The next thing to do is to collect the like terms involving the similar differentials. So here I have a dx, and here I have a dx. What I'm going to do is collect their common coefficient. I have 1 minus u, 1 minus u. I have minus u over here, so another minus u here. The other one will just distribute the minus x to give me the minus x with the du. So really it's 1 minus 2u dx and then minus x du. And if you've done everything correctly at this point, you should have a new equation. It has a different variable. Instead of y, it has u. And you should be able to separate this equation now. And in fact, if I bring the other term to the other side, the x du over to the right-hand side, and then do some division, I notice now that it's completely separated. So I'm going to integrate both sides, and I'll have the natural log of x on the left, and essentially a natural log on the right. It's linear down here, so it'll be natural log of 1 minus 2u. But I have to do a little bit of an adjustment here. If I was to differentiate this right now, I'd get a factor of -2, so I'll need to divide by negative or multiply by -1/2 there to account for that. And essentially, we've solved this this differential equation now. Unfortunately, it's in terms of this variable u, and I certainly haven't obtained an explicit solution at this point. So what we're going to do next is solve for u, which is of course y over x. Everything has a log in it, so I'm going to rewrite the thing that I'm interested in, the log with the u in it on the left hand side. So I brought the -2 over to the right. And I'm then going to exponentiate both sides. Well, before I do that, actually, in fact, I'm going to take that -2 and write it as a power, so it'll be 1 over x squared here. And now I'm going to exponentiate both sides of this expression. So what I mean is I'm going to use this as a power of e, and when I do that I'm going to have 1 minus 2u in absolute value, and I'm going to use that right hand side over here as a power of e as well, as an exponent, and when I do that I'll have e to the c. Because I'm adding, it's going to be product of the exponents, so it'll be e to the log, which will be the 1 over x squared. So I now have essentially some constant here, e to the c. I'll call that a, and I'm dividing by x squared, so a here is just the e to the c. That's some positive number. So if I want to get rid of the absolute values, I have 1 minus 2u without the absolute values could be some positive or negative number on the right hand side now. So plus or minus a over x squared. And we'll call that new number b. b is just plus or minus a. And we've made some good progress here. Now we're fairly straightforward to solve for u at this point. I'll take 2u and solve for that, and if I rearrange things a little bit, I'll have 1 minus b over x squared, and I'll divide, well, actually I found a common denominator here, and I have x squared over x squared for 1, and so I'll have x squared minus b over x squared. And now I can divide everything by 2 in order to solve for u. Keep in mind u is y over x. So I'm almost solved for y here. If I multiply both sides by x to solve for y, I'll cancel out a power of x that's in the denominator to get a 2x in the denominator now. And now I have an explicit solution for y. Notice here that b is any non-zero number. Notice it was plus or minus a. So that means it's positive or negative, because a came from some exponentiated number, which is strictly positive. So b here can be any number you want that's not 0. And this gives us a general solution to our differential equation that we started with. Now you may ask, what happens when b is equal to 0? Is that also giving a solution? So I'm going to plug b equal to 0 into this expression. When I do that, y is equal to 1/2 over or times x. And its derivative then is just 1/2. And so I'm going to check whether or not this value of y satisfies this differential equation above. So I'm going to plug into the right hand side of the differential equation what my y is. So x minus y over x is equal to x minus 1/2 x. I'm putting that in for y. Simplifying. And so when I'm done, I get 1/2, and 1/2 is just dy dx. So in fact, plugging that particular choice of y in for, that 1/2 x in for y, agreed with its derivative, and so it really is a solution to this differential equation. And this is called a singular solution. When b is equal to 0, this is called a singular solution because it didn't come about from our general analysis that we did throughout most of this problem. We did a general solution by doing all of this work here, and that gave us this case. And then there's this one-off kind of singular solution that results from a specific instance of the analysis, and that means we can basically replace this and say b can be any constant, and this gives us now a complete general solution to the differential equation.